All right, so let's get into the circuit analysis procedure here using Laplace transforms. Of course, we already talked about this, but the procedure is we take a time domain circuit, we take the Laplace transform of the circuit or of its equations, we convert that into the S domain, or the Laplace transform converts that circuit into the S domain. We solve the circuit in the S domain, and then once we get the S domain solution, we convert that solution back to the time domain using the inverse Laplace transform. And that procedure is outlined here. In this video, we're going to talk about step 1. So let's take a look at this circuit. Step 1 is basically applying KVL and KCL or KCL to obtain, they call it an integro differential equation. That means it basically is an equation that has derivatives and integrals in the equation, and we're going to see that for this circuit for time t greater than or equal to 0. So in this case, they're modeling this as a circuit with a 1.6 volt source that with a switch that closes at t equals 0. So what that's basically going to look like is nothing, 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 and then at time t equals 0, it's going to jump up to 1.6 volts. And that value is basically V0. So they're just saying that we can basically represent this entire source as a unit step function multiplied by V0, right? Because it's basically nothing, and then it jumps up to a value V0 at time t equals 0. So we could redraw the circuit, and we can say we have a unit step input, and we can call it V0 times U of t, connected to a resistor, capacitor, and an inductor. Of course, the values are all given. Let's just keep it in terms of C, R, and L for now. And basically what we want to do for this particular circuit, let me see, I think that they want us to find I of t. I think that's what the problem is actually asking us to do. Unclear, but let's just assume that that's what they're asking us to do, is find I of t. Okay? So we're going to write out the expression for this circuit. Let's call this circuit, or this loop current, I of t. And of course we know how this all goes. This would be a KVL where I can write V out, or V0 times U of t, minus the voltage drop across the resistor, which is going to be I of t times R, minus the voltage drop across the capacitor, minus the voltage drop across the inductor. But we know the voltage drop across an inductor, V is equal to L di dt, so we can write that L times di of t dt, and this whole thing is going to equal 0. Now, we have two variables here. We have I of t and we have Vc of t. So we need to get rid of Vc of t, but we can do that. We know that Ic of t is equal to C dVc of t dt. And so all we have to do here is divide both sides by C, multiply both sides by dt, and we get a differential equation here, 1 over C times the integral from 0 to t of Ic of t dt. And then of course we have to, because this is an indefinite integral, we need to add a plus c here, like our constant of integration, but in this case it's just going to be the initial condition on the capacitor voltage, okay? And so this is going to be equal to Vc of t. And so I can rewrite this expression here, V out times U of t. I'll add all the terms over to the other side as well, I of t times R, minus my big expression for Vc of t, which is going to be 1 over C integral from 0 to t of Ic of t dt, plus this initial condition, Vc of 0 minus. And then we can close that square bracket, plus L di of t dt. And we can say that that is our expression. Okay, so this is our integro differential equation for the circuit for t greater than or equal to 0. So this is where we're at. This is step 1. We are set up to move forward. Of course, we could plug in values, but there's really no need to do that yet. And this is step 1. So let's just take a nice little box around this so that we know that that's the completion of step 1. Okay, and we'll just write step 1. Check. And so in the next video, we're going to go into step 2. Of course, this is not a solution by any means, but this was the goal of this slide, was to obtain the integro differential equation for the circuit. So this is the equation for that circuit. You can see that there's a derivative in here, there's an integral in here, and so Obviously, this doesn't look like it's very fun to solve, but what we're after is I of t. So really, I could replace this IC of t with I of t because the circuit is a series circuit. So every single one of these is the same current. So let's just leave that like that. And we will call it a day on this video. In the next video, we will take a look at step 2.